In this lecture, we will talk about CPU scheduling. It is one of the more interesting lectures about how we schedule the CPU to execute multiple processes. The agenda for this lecture is we'll start talking about motivation for a good CPU scheduling algorithm. Then we'll move on to what a CPU scheduler is, the goals of a CPU scheduler. Later, we'll talk about various algorithms. We'll also talk about priority and round robin scheduling. And while we are dealing with all these algorithms, we will work through many examples. So recall from our previous lecture this process state diagram where we show the general life cycle of a process when it newly gets admitted to when it gets terminated. So for example, if a new process comes in, it is admitted to the ready queue, and once we have a processor ready for that process, then the scheduler dispatch is going to allocate a CPU to that process. And once that happens, the process is going to start running. And while it is running, multiple things could happen. For example, if we have a IO or input output operation request or an event for which we need to wait, we might go into a new state called the waiting state, and we will stay there until that input output operation or the event is completed. And once it's completed, we go back to the ready queue when we continue to wait for a processor. If we are right now running a particular process, we might get an interrupt which could again move us back to the ready state, which means we are again waiting for a processor. Or if a process is complete, then from the running state we might exit and go and terminate that process. So all of these transitions from one state to the other, we are going to have to make sure that the CPU scheduler makes good decisions, because the CPU scheduler is making a decision each time there is a transition from one state to the other. So we'll take a look at some algorithms for CPU scheduling that allow us to make good decisions, and we'll see what we base those decisions on. So before we get started, I think it's very good to look at some definitions. So for example, the arrival time, exit time for a process, response time, burst time over here. So let's go through these definitions. So arrival time is the time at which a process enters the ready queue. And ready queue is the state ready that we looked at in the previous process state diagram. So the time at which it enters the ready queue is called the arrival time. The exit time, on the other hand, is the time at which a process completes its execution and terminates. So that's when the process goes to the terminated state. Response time is the time spent in the ready queue to get the CPU for the first time. Notice over here this is specifically for the first time, because there might be multiple times we could get the CPU. So for example, if there is a IO operation request, then we go back to the ready state for the second time. So this response time definition or calculation is based on the time spent in the ready queue to get the CPU for the first time. This is for a process. Then the burst time is the total time taken by a process for its execution on CPU. So how long did we run this program on the CPU? Typically, this burst time can further be classified into CPU burst time and input output or IO burst time. Generally, we refer to it as the CPU burst time, and we'll talk more about those details when we get to discussion on burst time in detail. But it's going to be the total time for a particular process for its execution on the CPU. Next, the turnaround time. So this is going to be the total amount of time spent by the process from coming in the ready queue for the first time to its completion. So when did you come to the ready queue for the first time until you complete, which means the process goes to the terminated state. This can be calculated by simply subtracting the arrival time from the exit time. Waiting time is the total time spent by the process in the ready state waiting for the CPU. This is the total time. So we are adding up all the times it was waiting in the ready queue. This can be calculated by subtracting the burst time from the turnaround time, and we looked at these definitions just a bit in just a bit ago. Next, we talk about quantum time. This is a fixed time slice that is assigned for each process. So when we talk about round robin scheduling, we will look at how quantum time or a particular time slice can help us share a system better. The last definition here is throughput, which is the number of processes that are executed by the CPU in a given amount of time. And clearly, we want to maximize the throughput while we minimize some of these times. For example, we may want to minimize the turnaround time and the waiting time, for example. Okay, so having talked about that, let's move on to the goals of the CPU scheduler. So this is the scheduler dispatch that we saw in the process state diagram. What are going to be some of the goals for a good CPU scheduler? So at each transition from one state of the process state diagram to the other, we are going to at least try to make some good choices. So for example, one of our goals could be to maximize CPU utilization, which means that I want to use my CPU as much as possible for as long as possible. I do not want my CPU to wait for certain things to happen. If I wait, then I might as well just go on and work on a different process. So maximizing CPU utilization is, in other words, increasing the throughput is one very good goal for a CPU scheduler. The other one could be to maximize the number of processes completing per second. This is directly the throughput. So the difference between CPU utilization and throughput is CPU utilization uh, is my CPU waiting or not. So we do not want to spend too much time in the waiting state. In terms of throughput, it is strictly calculating how many processes are getting completed in a given amount of time. The next goal could be to minimize the average turnaround time. Another goal could be to minimize the average waiting time, and the last goal, or this list continues. This could get larger. Another goal could be to minimize the variations in response times. So, for example, if we want to have a more consistent response time for processes, then we want to minimize the variations in those response times. And this is going to depend on the kind of CPU scheduling we use as a CPU scheduling algorithm. Notice over here that the optimizing for different metrics could be conflicting to each other, which could lead to compromise and trade-offs. For example, to maximize CPU utilization, we may not want to carry out context switch too much, which nevertheless could hurt response time and waiting time. Okay, so with this, we will get into the basis for scheduling. What should I use as my basis? A process execution alternates between bursts, and those bursts can be classified as CPU bursts and IO activity, input output activity, or IO bursts. So CPU burst is CPU burst is the time that the CPU is running on a particular process, and IO burst or IO activity is the time that process spends for input output operation to complete. So in general, you will have a process that alternates between a few CPU instructions being executed, or CPU running some instructions, and then we wait for some IO to complete, then we go back to the CPU burst, and then alternate back and forth until the process gets completed. Now, the CPU bursts, durations, the duration of CPU bursts, they are extensively measured. And after people measured those burst times, it was found that they vary greatly among processes and computers. And they invariably tend to have a pattern. And in a little bit on the next slide, we are going to look at what pattern those CPU bursts have. We are going to observe the relative frequency of each burst duration. So, how long does a typical burst duration last for? So, we are going to take a look at that. And the distribution that we are going to observe is uh, an exponential distribution or the hyper exponential distribution. So once we take a look at the distribution itself, you will be able to relate that to the terms exponential and hyper exponential. So on the next slide over here, we look at the distribution of CPU burst. On the x-axis, we have the burst duration in milliseconds, and on the y-axis, we have the frequency, which means that the number of CPU bursts are on the y-axis. And as you can see, there are a large number of CPU bursts that have a very short burst duration, and that peak is typically around a 3 millisecond mark. So many short bursts, and these are bursts of programs that are currently working on, well, the CPU is working on them, and they may, because we know that it alternates between CPU and IO, they are probably going to be IO bound programs. And then there are going to be fewer bursts that are longer, so more than 8 milliseconds, for example. These are going to be bursts that are for typically for the IO burst. So these are going to be processes that are CPU bound. So after they complete the IO, they are bound to go back to the ready queue waiting for a processor. So we can we see this pattern, and that distribution is with a very strong very high probability of being close to 3 millisecond. That kind of distribution is called the exponential or hyper exponential distribution. And once we know that there is a pattern, then we can use this 3 millisecond number of a typical burst duration to design a good scheduling algorithm, now that we know the pattern. So we'll take a look at those scheduling algorithms in the next part of the lecture series.